So what we're doing in this section is we're going to be talking about something called titration curves. Titration curves are the graph or is the measurement of pH while you're adding the titrant to the solution. And it's going to have a graph shape that looks something like this. This is going to be volume of titrant. And then as we do the titration, you're going to see specific shapes come up on the graph. And if you're looking at them for a weak acid, they often look something like that. Okay. And so what we're going to do in this section is explain like why it's this shape. And we're also going to spend some time doing calculations so that you're able to calculate the pH anywhere on that curve. So before we really get started on that, I thought it might be useful to sort of talk a little bit about the process of titration and then show you some videos of a titration being done and just some titration calculations. So before we get into the videos, I wanted to set up what we're trying to do in this particular experiment. We have a solution of sodium hydroxide in a burette and we want to know what its molarity is. And so we're going to be titrating a sample of oxalic acid dihydrate with the sodium hydroxide that's in the burette. And these are the masses and volumes, but I'm just going to run the videos really quick to remind you how it's done. And then we're going to calculate the molarity of this solution that's in the burette. And if you remember, molarity, right, is just moles over volume. And so this volume that we get here, that's the volume of the titration. That's the sodium hydroxide volume. This number of moles will have to come from this mass through a quick mole conversion and some stoichiometry for the chemical reaction. Now, in this particular titration, the chemical reaction, the titration reaction, is NaOH plus H2C2O4, and that's going to give us, and if you remember some of the tricks I was trying to show you in the last chapter for balancing these, there's two H's and one OH, so it's going to be at a 2-to-1 ratio. I actually already know at this point, well, it really skipped a lot. Two NaOHs here. The product will be sodium carbonate and water, or sodium oxalate and water. And there'll be two of these as well. And just one sort of side note on this. When you're doing these calculations, this sample comes as a hydrate, but what actually reacts when you place it in water is these break off the crystal structure. So really this is all that's reacting. So sometimes this form of the material confuses people, but you need to have this formula because that's what goes with this mass. And then once you figure out the moles of this material, then it's a 1-to-1 correspondence to the oxalic acid in the dihydrate to the oxalic acid in the solution. So let's take a look at the videos. So I've sped this up a little bit, but typically for careful work we do mass by difference. So we tear out a piece of weighing paper. We add the amount of sample we believe that we'll need. Record its mass. That's what you saw on the slide. We dump as much as we can off the paper into the flask, and then we reweigh it to catch the residual that didn't come off the paper. All right. So again, I've sped this up, but when you record that initial volume. There's a sample that we just looked at with a little bit of water. If it's solid, you add water to it. If it's a liquid, you don't have to. And then an indicator was also added. In this case, it's phenolphthalein. And this is a standard technique for titrating the first sample. If you're looking at the second sample, typically you know how much to add roughly, and so you go ahead and add that. Very much the way we've done titrations already in the class. And then as you get close, you can go a drop at a time, or you can spin the burette like I tend to do. Just so you know, I still love my wife even though she titrates like that. So there you go. that would be the endpoint. And the important part isn't the exact color, it's really the consistency. And then what you do is you record the value on the burette. And again, just because people were doing it a little bit incorrectly, this is 16.45 roughly, 46 at this point here. And this would be 16.5, right? So it's going downwards in this direction. So from that, we can do our calculations and calculate the molarity of our solution. Okay, so we need our volume in liters. So we can go, I'm going to show you two ways to do this actually, but you're going to get liters is the unit you want. So I usually write the unit to the left and say equals, and I go 16.16 mLs. And then we're going to convert, and we're going to say, you can either say 1,000 milliliters for a liter. That's what a lot of people are used to saying. I've always taught in 3, it's 10 to the minus third liters. That's 1 ml, because m and 10 to the minus third mean the same. So that becomes 16.16 times 10 to the minus third liters, and then you would convert that over and write 10 to the minus 2. Okay. The other way that I've often taught students how to do milliliter to liter conversions is to simply do this, 16.16 milliliters, and then you just cross this out and write 10 to the minus third. Okay. And that's usually a pretty simple way to do it. And then you can just enter it like that in your calculator when you're doing your calculations. It doesn't really matter. So we've already figured out the bottom half of our calculation. So we're going to just say 16.16 times 10 to the minus third liters, or you could rewrite it like I'm showing here as 1.616 times 10 to the minus 2. It means the same thing, so it doesn't really matter how you present it in your calculations. So the next thing to do is to go to moles, right? And so moles is going to be starting with our sample mass, 0.1034, and to get that, what I did is I took my first mass and then I subtracted the residual mass on the paper, and that gave me this final mass here. Now the molar mass, that's grams, and then it's 126.07 grams for every 1 mole. And I just got that by adding all this. This is the 126.07 grams per mole. And that's of H2C2O4. And then it's 2 moles of NaOH. I've gotten that from here, right? For every 1 mole of oxalic acid. And I'm just going to call it H2A because I'm out of space. And you do that calculation, and you should get something on the order of 1.64036 moles of NaOH. Now we were trying to make this solution to be 0.1 molar, so it's actually pretty close. So it's going to be times 10 to the minus third moles of NaOH. And so 1.6403 times 10 to the minus third moles, and you do that calculation, and that comes out to be 0.1015 07 molar, or 0.1015 molar, rounded. Okay, 4 sig figs in the calculation. There's 4 in this mass, there's 4 in this volume, there's 5 in this molar mass, and so you end up with 4 significant figures in your calculation. And as a general safe rule, I've always been telling you guys probably 3 significant figures is good for most answers, but in titration problems, typically it's 4 or sometimes better, depending on the amount of material you're titrating.